So if z equals 1, if we put z equals 1 into this expression, we get what are called the nth roots of unity. Unity is just another word for 1. So we get, obviously, r equals 1 and theta equals 0. So we end up with e to the I 2 pi m over n. We'll keep m going from 0 up to n minus 1. So we can write that in, so what do we get when we substitute in these values? Well, we'll get 1 e to the I 2 pi over n, e to the I 4 pi over n, all the way up to e to the I n minus 1, 2 pi over n. So we can rewrite that in a sort of more compact way if we let omega n equal, omega n equal e to the I 2 pi over n. Then we can write this as 1 omega n squared all the way up to omega n to the n minus 1. So this basically means that for any complex number, z now, if we let z naught equal the case when m equals 0, so suppose z naught is okay, so the m equals 0 case in this formula. So now we're looking at finding the nth root of z naught to the power n, I guess. Then we can write that as the nth roots. So if I say what we're doing now is the nth roots of z naught to the n. Then they will be z naught omega n, z naught omega n squared, and so on up to z naught omega n to the power n minus 1. So in fact, you can construct any set of nth roots of any complex number by taking the first root, so I call the first root the one when m equals 0, and then multiplying it by what are these called these nth roots of unity. Okay, these quantities here. Now obviously these quantities here are of the form e to the I theta, which means they have magnitude modulus 1. And basically all you're doing to get the next root is multiplying by e to the 2 pi n each time. So this is multiplied by, this is z naught, then I multiply it by e to the I 2 pi n, multiply it by e to the I 2 pi n again. So I'm rotating by 2 pi over n each time until I get back to where I start. Here, if I rotate by 2 pi over n again, then I'll get omega n to the power n, which is just a full rotation of 2 pi. I get back to where I start. So we have a geometrical picture now. So for example, if n equals 5, then what do my fifth roots of unity look like? Well, I have 5 of them. 1 e to the I 2 pi over 5 here. That's omega 5. And then that one's squared, which corresponds just to rotating it by 2 pi over 5. This one cubed, omega 5 cubed, again rotate by 2 pi over 5. Omega 5 to the power 4, rotate by 2 pi over 5. Then if I rotate again by 2 pi over 5, then I get back to where I started. Okay. So these are the 5 fifth roots of 1, or fifth roots of unity. Now suppose I want to find the fifth roots of a complex number z. Then I can use this formula here, where z0 is my complex number, the first root of the first fifth root of the complex number. So in that case, if my first root is here, for example, this is my z0, then basically what happens is that I multiply the z0, that's my first root, to get the next root. I multiply by omega 5, z0 omega 5. Then the next one I multiply again by omega 5, and I get z0 omega 5 squared. And then the next one I multiply again by omega 5 and get z0 omega 5 cubed. And the last one, again, I multiply by omega 5 and get z0 omega 5 to the power 4. So the thing you notice, of course, geometrically, the roots of unity lie on a regular n-gon, in this case a pentagon. And similarly, for any complex number, the nth roots will also lie on a pentagon as well, regular pentagon, but this time it's rotated. Obviously the first fifth root or nth root of 1 is 1 itself. Okay. In general, for a complex number, this pentagon will be rotated relative to the roots of unity, but the shape stays the same. And obviously the size of the pentagon depends on z0.